Okay, so today is going to be on the photometric systems, and emphasis is going to be on the fact that there are two main photometric systems that are in use today. One is called the Vega system, in which the standard for comparison, or in other words, the 0 point for all filters, is the spectrum of Vega. You know, what measurement do you obtain if you measure Vega through a certain filter? That's the 0 point. The other one is called the AB system. I have no idea what AB stands for. I shouldn't have that on film. Probably have my PhD revoked. But it came out of Caltech, and it has now become basically the industry standard because it's based upon a theoretical spectral energy distribution that is very simple, and therefore is not subject to uncertainties due to measurements and things like this. Okay, so the AB system is the new one. The other aspect of a photometric system is not the comparison or calibration energy distribution, which I just told you about the two, the Vega system and the AB system, but then you have a system of filters through which you measure the brightnesses of astronomical objects, including stars. And these set of filters then have their own transmissions. So they have a certain percent of the total light coming into them that actually makes it through the filter. They have a function to their sensitivity. It's a function of wavelength. So you have to account for the throughput, if you will, and the wavelength dependency throughput of the individual filters in a given filter system. Now, the filter systems that we'll talk about today are called the Johnson UVB, started in 1953, the Johnson Cousins, which is basically an expansion of UVB into the red and infrared. And then for stars, because this is a stars class, the Stromgren UVBY system came up in '66. These are very narrow, non-overlapping filters. And then probably the most standard and modern one that you have today is the Sloan filter set. And most observatories seem to be adopting the Sloan filter set. Again, came out of Caltech. Very, very intelligent gentleman, James Gunn, part of the designer of the Sloan Digital Sky Survey, designed the filter set, etc. He's now at Princeton. Maybe you've heard of the Gunn-Peterson effect. When James Gunn was a young graduate student, he sat in on a talk, which somebody said, "We discovered a quasar at redshift 2." He walked away from that talk, and with a fellow named Peterson, by the end of the afternoon, had derived the Gunn-Peterson effect, showing that you should be able to measure the opacity of hydrogen in the universe cosmically from these quasars. Published the paper, came out a month later, and they did that as graduate students, just listening to a talk, talking in the hallways. I know, makes me feel like an inadequate astronomer, but there are people out there like that. And then there's a bunch of more minor systems, and we're not going to get into those. So the filter systems are basically honed-in systems which allow people to try and measure some basic physics about stars. For example, their metallicities, or what their temperatures are, or, for example, how large the Balmer break is, to get something about measuring pressure, temperature, and density, surface gravity, something like that. Okay? So we're going to talk about that. So again, to review, photometric systems, Vega 0 point or AB 0 point, and then multiple filter systems, Johnson Cousins, Stromgren, and Sloan Digital Sky Survey. Okay. So basically, like I said, each system is designed with certain target measurements in mind. Okay, so let's look here at the Johnson Cousins Vega system right off the bat. Okay. Now, if you remember, in the optical, this part of the spectrum where you see the bound-bound transitions from hydrogen, okay, H alpha, H beta, gamma, delta, epsilon, etc., is called the Paschen continuum. These are photons which can ionize neutral hydrogen that's in the n equals 3 state. In other words, from the Paschen state, n equals 3. These photons can all ionize n equals 3 bound neutral hydrogen. So they call that continuum the Paschen continuum. And in the Paschen continuum, you see the Balmer bound-bound transitions. And then you get to the Balmer continuum, photons that can ionize from the n equals 2 state of neutral hydrogen. Now, this is the ionization edge we talked about. These photons have exactly the right energy to knock an n equals 2 electron off of a neutral hydrogen, and it's called the Balmer jump. Okay. This is an A0 luminosity class 5 main sequence or dwarf star. Okay, and in fact, this spectrum is that of Vega. Okay, which defines an A0 V or 5 star. Okay. Now, so ultraviolet technically starts here below about 3,000, 4,000. Okay, that's what the U band means, ultraviolet. It's not technically ultraviolet. Ultraviolet's a little bit lower. Then you have the visual band here, which is sort of defined between 4,000 and about 7,000. These are optical astronomer definitions. They're kind of antiquated, all right? And then the infrared out here, above 7,000. Now, technically today, as a quasar absorption line spectroscopist, I think of 3,000 angstroms as the UV cutoff, and I think of about somewhere between 9,000 and a micron here at 10,000 angstroms as the cutoff to the ultraviolet. Okay. All right. So U band is this filter. You can see that it has a very steep sensitivity function peaking here, and then the sensitivity decreases. And that overlaps with the B band filter, which when you just let light through, if you let through a uniform light source, okay, that has equal intensity at all wavelengths, then the intensity will follow this curve. There's very, very few photons get through, and then peak number of photons would get through, and then fewer. So that's what's showed on this curve is sort of the normalized transparency, if you will, at a given wavelength. So effectively, at the peak, all the photons in your flat source would get through, and as you come off the peak, say 80%, 50%, that's what the efficiency curves are. Then you have V here, around 5,500. This is centered about 4,500. This is centered around 5,500 angstroms. And you can see that it's not symmetric in its sensitivity. And you can see that the B band and the V band overlap, which is kind of a bad thing about your system. What you'd really want is something that's kind of flat, it doesn't overlap, so that you can really separate out these regions of the spectrum. Okay. Then you have R, which is even more elongated, so it doesn't have as good as a high-pass filter, as a less efficient high-pass filter, and then the I band. Okay. And you can see that each one of these is designed to measure a certain region of the Balmer jump or the Paschen continuum. Okay. So the I out here and R and V really get the Paschen continuum. And then you have the B band here, which is getting this area where you start to get close to what's called the Balmer convergence, where the lines of the bound-bound transitions are getting closer and closer and closer together. And then the U band actually is centered such that it's basically collecting flux blueward of the Balmer jump, flux that's in the Balmer continuum as opposed to the Paschen continuum. Now, I've been throwing out a lot of technically precise statements there, and hopefully all those words are coming together. Balmer continuum, Paschen continuum, Balmer convergence, Balmer jump, okay, et cetera, et cetera, et cetera. Okay. Okay. Now, I keep thinking my notes are over here. move to the next one. So how do you define a magnitude? Okay. So magnitude is basically a measurement of an integral, and the integral is of the. I'm going to introduce to you now some terms. The flux density, and when you do the integral, you get out something called the flux. Okay. So let me define these two terms, flux density and flux. But the magnitude itself is the ratio of the flux in the band of the filter, that of your target object divided by that of your standard. Okay? You take that ratio, you take the log of it, base 10, multiply it by minus 2.5, and that gives you what's called the apparent magnitude. Okay? Okay. If you're using the Vega system, this is the measurement of the flux of Vega through that band. Okay, magnitude for that band. And this is the flux of the target star through that same band. Take the ratio, log it, minus 2.5, get this measurement of the magnitude. Okay. So what is the flux in the band? Okay, that is the integral over the filter of the flux density times the transmission of the filter. Okay, so the flux density is the true spectral energy distribution of the star. It is the flux at a fixed wavelength. Okay, it has units. Okay, I'm going to make a distinction in this class, and you won't see the distinction everywhere, because that distinction is interchanged. The capital F's and little f's are interchangeable between authors and subfields. But I'm going to try to maintain a standard for this class, which is that which I'm calling flux density is little f, and that which I'm calling flux, which is an integral term, integrated term, is capital F. Okay? The flux densities I define here in the box. Okay? This is the energy per second per square centimeter per unit of angstrom. It's a monochromatic flux. Why we call it flux density? Because it's flux, but it's monochromatic. Some people will call it the monochromatic flux. Some people will call it the flux density. I'll be calling it the flux density. It is in a Gossamer thin wavelength, color, monochromatic. In that exact wavelength, the energy per unit time per square centimeter that you measure. Okay? Per unit wavelength. You can also do this in terms of frequency, f sub nu, okay, in which case it's the ergs per second per centimeter squared per hertz, okay, per cycle per second. Okay. All right. Now, having defined that, the flux in the band is the flux density convolved with, I should say, modulated by the sensitivity. So let's say the flux density is a flat function. That's not going to work. I'm going to turn the light on for this. So fear and loathe not if you're watching this on the camera. So here's wavelength. Let's say this is the flux density. Okay? Let's say your flux density is a constant. At this wavelength has that F lambda. At this wavelength has the same F lambda. Let's say you have constant flux density. F lambda equals a constant. Okay? Then you have the sensitivity of the filter. Okay? Which goes from 0 to 1 transmission. Well, let's call that 1 transmission. Call that 0.5. And let's say it goes something like this. Okay? What is going to be the shape of the flux you measure? It's going to be exactly equal to the shape of the filter. And it's going to have this number is going to end up equaling that constant. Okay. What I'm trying to say is that the integral you'll be doing is you're multiplying this black line by that orange line at every place in each d lambda, and you're integrating it. So here's the black line, you multiply it by the green line, or the orange line, you get the green value. So this is the function you're actually integrating if your flux density was constant, right? But if your flux density was not constant, let's say your flux density did something like this. Nice little power law, okay? And you've got your filter here, which is doing this in shape, okay? So what's the final going to be like? It's probably going to, oh gosh, dear God help me, it's going to come up and do something like this. Like that.
So the green is the...
So the green would be the multiple. F lambda is the black power law. R of the filter is the sensitivity function of the filter, that's the orange. And then if you multiply these two curves together at each wavelength, that's my attempt at doing that, probably wrong. That multiplication, that's the integrand that you're integrating to get the flux. You see, so basically you have a spectral energy distribution which has a energy per unit time per square centimeter at each wavelength. Okay, you have a filter, you multiply the two together, you get out now a modulated flux density, the green line. You integrate that, you get the flux that was measured in that band, the integrated flux. Okay, and since you've integrated over wavelength, your capital F now has units of ergs per second per centimeter squared, which is your normal unit of flux. Ta-da! Okay. Now, here's the deal. If you get a filter sensitivity function, it'll be a table of numbers. Wavelength number, wavelength number, wavelength number, wavelength number, wavelength number. And it'll probably say wavelengths, 3,000, 0, 3001, 0.0001, 3002, whatever. And it'll go up, and you look at where it peaks. Okay? If it peaks at 1, then it's a filter. Those data are what are called a relative sensitivity function. I've been showing you those that are at 1, right? Here's a filter, and it goes like this. And if I gave you this as a table of numbers, the peak number you would see as you scroll down the table would be equal to 1. Okay? You can't use those data as are to get this right, because in order for this modulation to not change the value of the flux, the area under this filter sensitivity function has to equal 1. And let me ask you a question. If I integrate this, if I do this lambda minus to lambda plus of r lambda d lambda, which is what this is, am I going to get 1? Nope. Heck, just this part of the integrand, that equals 1. Plus I'm going to add 0.99 plus 0.98, blah, 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 blah. I'm going to get a value that's like, I don't know, 3.7, something like that. Nope. Can't use the data that way. You have to use them so they're normalized, so that this filter is normalized. Let me show you what a filter looks like if it's normalized. Here's 0 to 1. The filter looks normalized if it does something like that. Now, if I notice the value at the peak is less than 1. Now, if I take this thing and I integrate it the area is equal to 1, okay? And then I can use it like this. So when you get a table, sometimes you'll go to a telescope and it'll say filter data, and you click on, you download a file. You can't just go and use it. You have to make sure that the data you're getting, are they data that show you the peak transmission at 1, or are they data that show you that it's the area is 1? You have to figure that out for yourself. If it's a good telescope and the team's being friendly, they'll have a little help file and they'll say, these are normalized, or these are to peak transmission of unity. They'll let you know. Okay? Sometimes they don't, but you got to be smart and don't just take numbers that people give you and start, jumping off cliffs with them, right? Does anybody know what the equation would look like if I gave you a transmission function that was not normalized? What this equation would have to be written as? Well, lambda minus lambda plus of r lambda flux density lambda d lambda normalized by the filter. So there's two ways to do it. You can make sure that this is the situation, in which case what you have to do is you have to multiply every value by a constant such that when you integrate it, it's 1, or you can just integrate it and divide your number by the value of what you get under the filter. Okay. Make sense to everybody? Okay. All right. Boom. Okay. Let's see. Okay. So let's look at some flux densities real quick. So here's some examples of some flux densities of stars. Here's wavelength, okay? And this is actual angstroms. This is wave number, so we're not going to do that. That's basically inverse wavelengths. But here is what it looks like with frequency, and here's what it looks like with lambda for this star. Why? This is F nu, yeah. No, this is taken from a book called Gray, and these are wrong. This is F nu, so write this in your book. This is F sub nu, little f sub nu according to our notation. Okay, little f sub nu according to our notation, and this is little f sub lambda according to our notation. This should look just like the picture that I showed you of Vega, right? Notice that it comes up in this sort of inverse 1 over x kind of look, and then you have the, okay, when you plot it, the F nu as a function of wavelength, it looks more like a power law. Okay. These are the same spectral energy distributions from the same star, plotted differently. One plotted in the flux density of F lambda per unit wavelength, one plotted in the flux density per frequency. So the shape of the spectrum you look at depends upon what flux density you're actually plotting it as. Okay? And in fact, this is versus wavelength. As you can see, you can plot it versus wave number and you get a different shape. You could plot it versus frequency and you would get even a different shape. So the shape you look at depends upon what units you're using. It's another point I really want to make to you. Okay? Most of the times in different fields, people have the default one they use. Radio astronomers, they call it S sub nu, and they plot it as a function of frequency. Optical astronomers, it's mostly F sub lambda versus wavelength in angstroms. You had a question?
Yeah, never mind.
Oh,
Figured it out.
okay.
Yeah, sorry.
Good. I apologize for the labels, but books don't always have everything right. Okay. All right. So, given this, you might say, well, how do I do this experiment? If I'm using Vega band, I suppose what I could do is I could wait for Vega to come up. I could take my telescope with my filter set, and I could take, observe Vega and very carefully measure its spectral energy distribution or its flux density, which involves calibrating a whole bunch of things. It is not easy to do. And then I could take my filter band pass, make sure it's normalized, or use this other equation and calculate the flux of Vega, and that would be my standard in that band for my telescope, for my observations. And then I'd point it at the star I cared about, redo the exact same experiment, calculate the flux here, take the ratio, blah, blah, blah. Got the magnitude of my star and apparent magnitude of my star in that band. Great. Okay, you can do it that way. Or somebody could go along who's a real expert at measuring these things, and they could actually publish for this telescope, for this filter, this is what the flux of Vega is. So you just look it up, okay, in some table. And maybe when I was starting in grad school, this was a big deal. This book called Allen's Astrophysical Quantities. You could go and look up, and you could find out what is the flux of Vega through a U-band Johnson-Cousins, filter, and it would give you the number. Okay. Nowadays, you could just Google it. Okay. The books like the Green Book of Allen's Astrophysical Quantities, gone by the roadside. Okay. Anyway, so now sometimes you've probably seen this for the Johnson's B filter. Instead of calling it M sub B, replacing band with the filter name, people just call it B. You've probably seen that. Okay. You can get the the standard in lookup tables. Okay. Now, I want to show you the relationship between the F lambda and F nu. Okay. What you want to do is you want to conserve energy in the interval. So you have energy per unit time per centimeter squared per hertz multiplied by hertz. What does that give you? Ergs per centimeter minus this, blah, blah, blah. That's going to be equal to, if it's per unit wavelength, flux density, times an interval of wavelength. Because what happens? You've taken F lambda, this quantity, multiplied it by lambda, what do you get? Okay, so this quantity, d lambda, is equal to this quantity times d nu. So that holds. This is a standard thing. If you have anything that is what one would call a flux density. Oh, it slipped?
Yeah.
Thank you for watching. Did it just slip, or?
No, it's kind of been
Slowly dribbling down. Huh? Okay. I wonder if this would help. Putting this on there. Okay, well, let's just keep rolling. Keep an eye on her, please, as you've been doing. Thank you. This is a standard fare. If you ever have anything where it's like per something and you want to convert it to something that's per something, just multiply it by the interval and then you can equate them. Standard tool in astronomy. Okay, solving for F lambda, you get C over lambda squared because basically F lambda is equal to d nu d lambda times F nu. D nu d lambda comes from C equals lambda nu, blah, blah, blah. Take the derivative. There's a minus sign in there, but who cares because that's just telling you about slopes, but absolute values. F lambda is C over lambda squared F nu. Okay. And likewise, F band is equivalent whether you use it in nu or whether you use it in lambda. Okay, standards. Again, Vega and AB. Okay, let's look at AB first. AB, there should be a box around this, and I apologize there's not. This is the definition of the AB spectral energy distribution or flux density. Okay. F nu equals 3.63 times 10 to the minus 20 ergs per second per centimeter squared per hertz. That is, it should be the 3 lines. That's the definition of the AB. So if you drew F nu versus lambda or nu, it's a constant. Okay? Now that's nice because that's a number you can always get your teeth around. You don't have to have somebody else measure at the telescope for you or measure it yourself. It's a number, it's a standard, and there you go from there. Now, if you apply this rule that F lambda is C over lambda squared F nu, this is what you get. F lambda AB is equal to, and I changed the units so they work out nice for you, 0.1092. Sounds like some famous year in history. Okay. 1066 and 1492 put together for you somehow. All right. 1092 over lambda squared, if it's in angstroms, ergs per second, blah, 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 per angstrom. Okay. You can drive that yourself if you want. You have to convert some centimeters into angstroms to get that constant, but that's the way it works. Okay. So, through the definition of this, when you take this number, F nu, okay, and you put it through B-band filter, you get for this number, okay, 48.60. So the equation upstairs simplifies to minus 2.5 log F band minus 48.6 M band. Okay, and actually this is true for all bands. Why is it true for all bands? Because it's flat. Voila! Your calibration number, if you wrote this out, this has been minus 2.5 log F band plus 2.5 log F band standard. Okay, the plus 2.5 log F band standard is the same number in every band for a constant flux density. Why? Because remember, this integrates to unity. Okay, so it's this. If this is a constant and this integrates to unity, what do you get out? Constant. Everybody see that? Pull that constant out, integrate this, but this is defined to be that, so you get the constant. Okay? Well, you take that, take the log of it, take minus 2.5 of it, you get 48.6, no matter what band you're in. And that, ladies and gentlemen, is called elegance and beauty. Thank you very much, Caltech astronomers James Gunn. Okay, everybody follow me on that? Has anybody seen that before? Yeah. Okay, is there anybody who hadn't seen it before? Because am I like wasting all your time up here? Okay, good. Glad to hear that. I'd rather be saying useful stuff rather than when is this class going to really start? Okay. So now, by definition, you might say, where did they get that number? Did they pull that out of a hat? You know, did they just like roll some dice? 3, 6, 3, 20? No. They defined it specifically so that if you measure the V band in the Johnson cousins of Vega, that you will get the same number if you measure the V band in the AB system with the Johnson cousins. Okay, so Johnson cousins filter, which is these V band. Okay, you measure Vega, which has, here's its F lambda, and you do the integral of this sensitivity curve with that F lambda, you get out a magnitude, or a flux, or yeah, you get out a magnitude, And then if you measure the same thing across the dotted line, is that equation that I derived for you, the 0.1092 divided by lambda squared. That's the dotted line. This is the AB f lambda, f sub lambda. The integral across that in the V-band and the integral of Vega across the V-band gives you the same answer. And that makes sense because they cross somewhere here around 5,500 angstroms, and there's more f lambda in the toward the blue than there is in the Vega. There's more f lambda toward the blue in Vega than there is in AB. But redward of the center of the fulcrum of that, there's more flux in the AB than there is in the Vega. So those areas are the same, and you get the same number. And that, ladies and gentlemen, is where 3.63 times 10 to the minus 20 ergs per second per centimeter squared per hertz came from. And you heard it here first, even before you heard it from John. But you will hear it from John again. Okay, now, when the AB system number was chosen, to the best knowledge of our ability, given what the V-band, Vega band, Johnson-Cousins magnitude was, this number gave you what was measured at the time. But as time has gone on, our measurements have gotten more precise, and that Vega V-band magnitude in the Johnson-Cousins has slightly changed. Okay, so here is a more modern version of that, and the V-band, you can see now the AB and the Vegas differ by 0.044 magnitudes. Okay, which is one of the reasons why AB has become the standard, is because Vega keeps moving around a little bit. So forget it. All right, do it off of the standard. It's rock solid. It's a brick wall. It's not going anywhere. Okay. Make sure I didn't bypass anything I wanted to talk about. Okay, so basically, again, I'm talking about this figure. There's Vega, there's the AB given by the wavelength version of the flux density. Okay, plot it up, and you get the same V magnitude. Okay, great. We talked about that. Now, what I want to do is show you the Sloan filters versus the Johnson-Cousin filters. Okay. Now, there's things that are great about the Sloan filters, and that is their sensitivities are much flatter. They're more like top hats. Top hats are much easier to approximate. Let's say you don't want to do a numerical integration of your data across some sensitivity function that's complicated like this, with some kind of sloppy high pass filter through it. Okay? You know, the low pass is nice and tight, the high pass is loose. Or the R band, the high pass is very loose. In fact, overlapping great amount of flux that can come through in the I band into your R band filter. Who needs that? So here they are. And the other thing is that you can almost now approximate that as a top hat and do these things on the back of your hand. Okay, the back of a piece of paper. Or even the front of a piece of paper if you want. Okay? But the point is they're more top hat, so you can almost just pull the sensitivity function out of the integral and just sort of add up your flux to get your flux, add up your flux density to get your flux. Okay, so these are much better in that sense. There's one that's called the Z band that goes out further into the infrared. Little I corresponding to I, R to R. Now, the thing about it is that the Sloan has this thing called the G band. It doesn't have a V band, okay? And the G band is more corresponding to what you might call the blue band. But when you look at the G band magnitude of something and you compare it to the B band magnitude of something, even if you're comparing A-B magnitudes, they're going to be different because the filters are different. You're picking up different regions modulated by different filter responses for these two filters. So guess what? There's a whole science of converting, Vega Sloan magnitudes to Vega Johnson-Cousin magnitudes, and also for AB. And you can see tables of those. And they call them color terms and things like this. Okay, you can look up those tables. John is a maestro at this. This is his thing. He's quite a world expert at it. Okay. All right, Johnson UVB. What is it there for? Why did they put those filters in those regions of the spectrum? What are they trying to learn about stars? That's our next phase in our discussion of magnitudes. Before we do that, are there any questions? So if I said to you, how many magnitude systems are there, how would you answer that? 2, Vega and AB. But within those, there's a series of different filter sets you can choose. So now we're at the different choices of filter sets, and we're going to say, why did people make different choices of filter sets? Why can't we just have one and be done with it? Because if you're looking at galaxies, you're looking for different things to measure than if you're just looking at certain stars. Okay? And you might actually, if you're looking at planetary nebula, look at something completely different. So filter sets can be designed because you understand something about the spectral energy distribution, and you know that you can get some quantifying differences in behaviors of the spectra, which is telling you something about physics, by looking in these different bands and comparing planetary nebula through these filters, different filters. You can learn something about planetary nebula. For example, but that filter set would be useless for using stars on because it targets, say, emission lines or something like that in the planetary nebula, which have no counterpart in stars. Okay, so you don't learn anything. So that's why. Okay, so we have the Paschen continuum. Okay, you just saw Vega, the Paschen continuum coming up from the infrared like this. You have the Balmer lines in it. Okay, that has a slope to it. Whether you do it as F nu or whether you do it as F lambda, it has a slope to it. That slope is very, very telling of the temperature of the star. Okay, so the Paschen continuum slope, and the indices for that are U minus B and B minus V. Let's take a look-see here. V minus B and U minus B, right? Are those the two? I'm not an expert at stars. UB, BV. BV. So what does that measure? Well, this one looks like it measures the slope pretty well. The slope's kind of flattened out through here a little bit, and this R band's got this horrible high-pass filterage to it. But the V and the B, there's not a whole lot of overlap, and you're measuring this region versus all this light through here. Notice that we're talking about all this light through here. So B minus V, pretty good. Measure that, if the star has a steeper slope, it's bluer. Okay, you're going to get a more negative number because magnitudes are negative. Well, absolute magnitudes are negative. You're going to get a brighter magnitude here and a dimmer magnitude here, and if it's wet. So pretty good. Okay. Then you want to use the U minus B as well because it tells you something about how strong this Balmer break is. Okay. And the Balmer break is also very temperature sensitive. Anybody remember why? This one, you're going to tell me the slope. Yeah, that's black body. Okay. There's also the H minus continuum opacity that carves that slope. But for the most part, you could argue T effective, black body slope. That I get. Okay. Does anybody remember why that drop is temperature sensitive?
Determines how ionized you are.
Determines how ionized you are. That's related to temperature, right? But also remember, as you get hotter, more of your neutral hydrogen atoms are in the n equals 3 state than in the n equals 2 state. So there's not as many hydrogen atoms to be ionized at this wavelength. So that as you go to higher temperature, the break gets smaller because A, more of your atoms are ionized, and B, more the ones that are neutral, the electrons aren't in the n equals 2 state anymore. Most of them up in the n equals 3 and 4 states. So those photons have nothing to grab onto and be absorbed by. Out they come. Okay? All right. So these two are really good indicators of your temperature. Okay? And a lot of times what people will do then is they will plot B minus V versus U minus V. Okay? And where you fall in this diagram tells you a great deal about what type of spectral class star you are. Spectral class. Okay. Gotta make sure I get this right. Class and then spectral type is V32118. Okay. So spectral class B, A, F, G, K. All right. So this is going toward redder. This is bluer. This is redder. And this is bluer. Okay. So I love astronomy. Toward negative numbers is bluer. Toward positive numbers is redder. Toward positive numbers is redder. Toward negative numbers is bluer. So this is the blue portion of the diagram. And then the red portion of the diagram is down here. And of course, yes, K stars, cool stars, and where you're bluer, in other words, where you've got a stronger slope, okay? Now, this little inversion is because the fact that the Balmer break maximizes in A stars at 10,000 degrees, okay? So as you go to cooler stars, the Balmer break decreases, okay? And you find yourself having a bluer U minus B. As you go to hotter, the Balmer jump decreases. You find yourself having a bluer U minus B. Right? Because you've got more flux in the U. It makes you more light with higher frequencies, bluer. Okay? You agree that if this is up here, the star is considered bluer. Right? So as you get cooler, this goes up, the star is bluer. A stars, it's maximum, and it's the reddest of these two filters. Of course, I've got the different Stromgren on here. I apologize for that. And then as you go to cooler, it's also same thing. I was just doing it with the different filter stuff. Your U minus B. You got more light coming through the U when you go to cooler or hotter. Therefore, U's larger. You got more blue light than comparatively, so you're bluer on the diagram. Okay. So B minus V is also sometimes called the color index. Okay. U minus B is also a temperature index, particularly for the early type stars. It's measuring the Balmer jump. Okay. Remember, the Balmer jump is temperature dependent, and as you get to cooler stars, it has some pressure dependency to it. Now, I'd like to ask if anybody remembers that. This is my favorite thing to quiz on. I'm going to ask it again and again and again and again. Yes, sir.
Can you say it again?
Balmer jump, I've just talked about its temperature dependence in terms of the ionization and excitations of neutral hydrogens, or of hydrogen. Okay? But when you go to early type, meaning hot stars, but when you go to the cooler stars, the late type stars, it becomes also electron density dependent. I'll write it down. I should get you all a shirt. Instead of a Superman triangle on it, should have a circle that says H minus. Okay. When H minus forms, it's a second electron on hydrogen. It can only happen in fairly cool environments. If the electrons are moving slow enough that a second one can get captured by a hydrogen, right? And when that happens, that electron has to come from something that lost its electrons, and those are the metals. So the metals donate the electrons, and the more electrons there are, and the higher the pressure is, the more chances of electrons being able to get captured onto these neutral hydrogens. Okay. I want to teach you to think a little physically too here, not just phenomenologically, but I know that you're drinking from a fire hose. Okay. But just remember, if there's anything you want to walk away from this class is the bomber jump is a maximum of A stars, and it depends upon why is it a maximum there? It's not just temperature. It's temperature and electron density from the H minus ion. H minus ion responds to the electron density. Okay. So basically, the U minus B gives you a little bit more information about the metallicity or the pressure in the star. Okay. But there's ways to calibrate that out. I'm just mentioning it. I'm not going to go through it. Okay, so that's Johnson. What about the Sloan? Okay, well, we already went through it that U and G are similar to U and B, and that G and R are similar to B and V. So at least for stars, okay, those are comparable, and you can make plots of what we call the color index in U minus G. I'm sorry, the color index B minus B in G minus R. All right. And it turns out now that these have become much more recognized and much more popular over the last 10 to 15 years, and I think the Vega system is probably on its way out. So my recommendation to you, no matter what type of astronomy you do, is quote AB magnitudes if you're going to talk about magnitudes in your work. Vega is dying. All right, last but not least, the Stromgren system. Okay, this is developed for stars by stellar spectroscopists. This is a new system that says, I don't like all the overlap in the Johnson-Cousins system. Okay, so let's make very narrow filters, and let's have it be very targeted, and try and get this information we were talking about out, the temperature and maybe the metallicity kind of indicators out much more cleanly. Okay? All right, so we have two indices that we use. Okay, before I said B minus V was called the color index. That's a standard astronomical thing. Okay. We have now some filters that UVY filters, UV, B, and Y filters, okay? So the U minus V is similar to the Balmer jump, okay? It misses the Balmer convergence entirely, okay? I'll talk about that in a second. Remember, that's where the distance between the bound-bound transitions before you get to the ionization edge get closer and closer. And unfortunately, the H delta Balmer line can complicate the color index. I'll talk about that in a second. Okay. Two indices, M1 and C1. So when you talk about Stromgren numbers, people will measure C1 or M1. Okay. C1 is basically the temperature sensitivity. I'm sorry, M1. Okay, hold on. M1 index is measuring of metallicity because it covers an area where a lot of metal lines show up, and then the B minus Y removes the temperature sensitivity. So this is called M1 because it's a metallicity index, okay? And it's the V minus B minus the B minus Y, where the B minus Y is calibrating out the temperature sensitivity. The C1 index is a measurement of the Balmer jump. Okay? It's U minus V minus the quantity V minus B. It measures the height of the Balmer jump. Okay? It skips the Balmer convergence very conveniently, which removes a lot of light in this one area just redward of the Balmer jump. And then the V minus B mitigates the metallicity sensitivity. Okay? That's being taught. U for ultraviolet, V for violet, B for blue, Y for yellow. And so what are they here? This is what they look like. Okay, here is a spectrum of a star, an A05 star. It looks to me like this is actually F nu. And then here is U, here's V, here's B, here's Y. You can see that they very, very narrow, very peaked, and don't overlap much. Okay, so U minus V measures the Balmer jump very well. See, the Balmer series is converging here before you get to the ionization edge. Here, see the convergence here, removing flux. If there was no convergence, that would still go all the way up and then come down on the ionization edge. But this turnover here is both the Balmer convergence and to some degree metal line blanketing, because a lot of metal lines are in this territory, and they also tend to reduce this flux. But by keeping this filter redward of this Balmer convergence and where the metallicity line blanking is, you can measure this much better. Okay? Does that make sense to everybody? Now, remember I said before that the H delta line can cause some problems here, and in fact, it's a poor 0 point. Is that the 0 point here is right on the H delta line. This is, let's see, 2 to 4, 2 to 5, 2 to 6 absorption. N equals 2 to N equals 6 absorption. Okay. Personally, I think he should have moved it over here a little bit, but then he would have some overlap, and he would have to push this over here, and then he's got H beta line getting in here. It's kind of, what are you going to do? Do it the best you can. Okay. So anyway, that measures the Balmer jump, the U minus V. The V minus B measures the slope, which gets rid of the temperature information. Thank you very much. Okay. So V minus B, Balmer continued decrement, U minus V. Okay. And then a lot of metal lines throughout here. Show up. Okay. So that is the Stromgren system. And if you look at the Stromgren system, for example, in this diagram, I guess I should. You guys must be happy because you know how close we are to the end now. Okay. This is B minus Y. This is the C1 index. B minus Y is the temperature going from cooler to hotter. Cooler. 0 is defined as an AV0 star. This is all Vega system. Okay. So AZ, okay, B minus Y of 0 is defined as the A0 star because it's on the, I forgot to mention this is all on the Vega system, not on the AB. You can see the C1 index is telling you that the Balmer jump is maximizing here at A stars. Okay. It decreases as you go to cooler stars. It decreases as you go to hotter stars. You already knew that, but there it is measured for you in black and white. Okay. So back in the day, when people were looking for ways to quickly look at a star and determine what's its spectral class and temperature and what's the strength of the Balmer jump to give them some indication about the metallicity and whatnot for that given, okay, they could plot it on this theoretical, it was basically a theoretical curve for perfect stars. They could plot the star, go, oh, it falls over here, therefore that's a G0 star. It's basically a quick and dirty way. You take 3, 4 bands through the Stromgren filters of a star, bam, you measure the fluxes, you do the magnitudes, measure the C1 index, B minus Y, plot it up there, you're good to go. Yes?
So those outliers on that plot, they're pretty far away from that continuum. Were they not main sequence, or?
Probably not main sequence, exactly. Probably white dwarfs. something like that. It's a good question. They clearly don't have any Balmer break. So that would, and then these are, actually that's a good question. Let's think about this. Right?
Well, with no Balmer break.
There's no Balmer break, and these are the 10,000 degree stars. That sounds like a white dwarf to me. They're sort of 10 between 10 and 20,000 degrees. And so then here's your hotter stars, no Balmer break. I'm going to go with white dwarfs.
So then would they be like, what about the stars up in the upper right corner?
You're asking me questions I never thought about before. Here you go. Very strong Balmer break, but cool. It's possible that when you get to something with molecules in it, that you see it break down. The Stromgren system doesn't work well. Maybe it's not a star. Maybe it was a quasar. Quasars don't have Balmer breaks, and they have a very blue continuum, so that's not so good because this would be a kind of coolish, reddish continuum. A Boscade beer for anybody who figures it out. That's a joke, by the way, even though that's on camera. Not a sincere offer. Okay. So anyway, that's the other thing. You bring up the points by asking the questions. What if you get a data point and it's way the heck off? A, I screwed up my measurements. I better go do them again. B, I verified it. That must not be a star in the typical sense of a main sequence or giant star. Ladies and gentlemen, I think that brings us to our last diagram, which is if you plot the V magnitude, absolute V magnitude, and I'm not going to get into how absolute magnitudes work. Okay, I think John will do that. Versus the color index from cool to hot, from hot to cool stars. And then you've got the, this is basically hot to cool, meaning from blue to red. Okay, the number going up, that's redder, that means cooler. All right, here's your main sequence, absolute magnitude, here's your sun. Okay, now, if you take the B minus V of what's considered to be an M star and it is a dwarf or main sequence, it will have 1.5 for its color index. But based upon, you remember the MK system, Morgan-Keenan system for spectral classifications and typing, that it used this two-grid system that used these absorption lines to do the actual classification and typing. Okay, so if you classify and type a star and you say, oh, that's an M01B, it turns out though that if you go and measure its color index, it will be a little redder. Okay, so the color index is not an exact indication of spectral type across spectral classes. Okay, so you can see, particularly with K stars, that a main sequence case 0 star, its color index is much bluer for a main sequence star than for the giant star. Okay, so the temperature, this is basically an isotemperature curve at some level, but it's telling you that the slope of the spectral energy distribution is redder for a giant star with the same temperature as a main sequence star with that same temperature. I think that's the good way to sum that up. So it's just for your FYI. You know, this is not something you're probably going to walk around with in your head for your research and for your, you know, you probably won't talk about this diagram again until someday you're teaching this stuff. Any questions? Wow, I finished the notes on time today. Don't get too excited on me here. Next for continuing to watch the camera.
Yes.